Welcome to lecture 12. In this week, we are talking about basic concepts of optimization part 1. In this lecture, we will talk about gradient and Hessian of functions, and we will also introduce the concept of convex functions and concave functions. These concepts have very important role in optimization theory. For example, the gradient of a function is 0 at a point which is a likely candidate for minimum or maximum. We call such points as critical points or stationary points. Similarly, the Hessian matrix of a multivariable function can be used to determine whether the function is convex or concave or neither concave nor convex. This also helps us to find out whether there exists a global minimum or global maximum. So, in today's lecture, we will learn about the gradient vector of a function, the Hessian matrix of a function, as well as what are convex functions and concave functions, and how do we determine whether a function is concave or convex. So, let us start with gradient vector. Consider a function of n variables f x. So, x is n vector. The slope of function f x at a point x equal to x bar is del f del x I x equal to x bar. The n vector of these partial derivatives is called the gradient vector of function f and denoted by grad f. So, if you have a function with n vectors, the gradient vector of the function will have components which are partial derivative of the function with respect to each variable. So, they will be del f del x 1, del f del x 2, del f del x 3 up to del f del x n. So, this gradient vector is a column vector. So, one more time, the gradient vector is nothing but the partial derivatives of the function. So, for a 3 variable function, your gradient vector will be del f del x 1, del f del x 2, del f del x 3, where the function has 3 variables x 1, x 2 and x 3. The gradient vector of a function f x at a point x equal to x bar is normal to the contour through the point in the direction of increasing f. So, this is an important statement. It says that the gradient vector always points in a direction where the function value increases most rapidly. So, if you consider these contours, so let us say this is the point which is x bar. So, the gradient vector will point in the direction of increasing function value. So, the gradient vector points in this direction as shown in the figure. Also, at point x bar, the gradient vector is normal to the tangent drawn at x bar on the contour. So, if you draw a tangent at point x bar on the contour, the gradient vector is perpendicular to this tangent line. So, remember, the gradient vector of a function at a given point is normal to the contour through that point, and it is always pointing in the direction of increasing function value. A point x star is called a stationary point or a critical point if at x star the gradient vector equal to 0. So, the gradient vector equal to 0 means that the gradient vector is a null vector. So, the each component of the gradient vector is equal to 0. These stationary or critical points may be extremum and are likely candidates for maximum or minimum. Let us take an example and find out the gradient at a given point. So, we take a simple two variable function 3x square minus 5y square and let us evaluate the gradient at point x equal to 2, y equal to minus 3. So, we have a two variable function. So, the gradient vector will have components del f del x 1 and del f del x 2. So, find out del f del x 1 from this expression, it is 6x. Similarly, del f del y is minus 10y. So, to evaluate the gradient at x equal to 2 and y equal to minus 3, you have to put the value of x equal to 2 and y equal to minus 3, and that gives you the gradient vector is 12, 30. So, the gradient vector has two components, they are 12 and 30. Note that if a function is a linear function, the gradient vector will be constant. You can easily find it. Consider f x equal to c transpose x plus alpha, where alpha is some constant. So, this is an expression for a linear function f x equal to c transpose x plus alpha. It is something like f equal to a x plus b. If you consider the function f equal to a x plus b and then take del f del x is equal to a. Similarly, you can express the linear function as c transpose x plus alpha. So, the gradient vector will be c, a constant. Now, let us discuss about Hessian matrix. Consider any n variable function. The following n square second partial derivatives can be written as in the form of a matrix. So, what are the second partial derivatives? You consider an n variable function. So, f x 1, x 2 up to x n. So, you have the first partial derivative del f del x I equal to 1 to n. Then we can have second partial derivative where again j goes to 1 to n. So, you will have n square components. You will have n square second partial derivatives. These n square second partial derivatives will constitute a matrix, in fact, a symmetric matrix which is known as Hessian matrix. So, we will have terms like del square f del x I del x j when I is not equal to j and del square f del x I square when I equal to j. So, for example, if you have a 3 variable function, you will have del square f del x1 square, del square f del x1 del x2, del square f del x1 del x3. So, this first row you have operated del x1 on del f del x1, del f del x2, del f del x3. Similarly, here you have operate del x2 on del f del x1, del f del x2 and del f del x3. Similarly, you have operate del L del x3 on del f del x1, del f del x2 and del f del x3. So, this 3 cross 3 matrix is Hessian matrix. Note that the Hessian matrix is symmetric, it is a square symmetric matrix. Why it is symmetric matrix? Hessian matrix is always a square symmetric matrix, because we have assumed f x is continuously differentiable, then the cross partial derivatives are equal. So, del square f del x I del x j is same as del square f del x j del x I goes from 1 to n, j goes from 1 to n. So, in other words, if you look at here, del square f del x1 del x3 is same as del square f del x3 del x1, because the function is continuously differentiable. Similarly, del square f del x1 del x2 is same as del square f del x2 del x1, and also del square f del x2 del x3 is same as del square f del x3 del x2. Here also you can say this and these are same, these cross partial derivatives are equal. So, the Hessian matrix is a symmetric square matrix. For a quadratic function f x, the Hessian matrix is a constant matrix. Again, you can show this easily. This is an expression for a quadratic function f x equal to half x transpose h x plus c transpose x plus alpha. So, first calculate the gradient, which is h x plus c, and then find out the Hessian, which becomes h. So, this is a constant matrix. Let us not confuse with this h and this h here. Let us call this A, a constant matrix, constant coefficient matrix. Let us take another example and find out the gradient vector and Hessian matrix for a two variable function. The function is f equal to x1 minus 2 whole square plus 2 into x2 minus 1 whole square. So, again it is a two variable function. So, the gradient vector will have two components, del f del x1 and del f del x2, which can be evaluated as 2 x1 minus 4 and 4 x2 minus 4. The Hessian matrix will be a 2 by 2 matrix. This is a symmetric matrix, and if you evaluate the second partial derivatives, you will get the Hessian matrix as 2 0 0 4 as components. So, to find out the gradient vector, you have to take the first partial derivatives, and to find out the Hessian matrix, you have to take all n cross n second partial derivatives. Let us take another example, f equal to x cube minus y cube plus 9xy. Again, two variable function, the gradient vector has components del f del x, del f del y, which are 3x square plus 9y minus 3y square plus 9x. We can also find out the Hessian matrix. So, find out all 4 second partial derivatives, and they can be found as 6x 9 9 minus 6y. Now, we will introduce the definition of convex set. A set of points or a region is defined as a convex set in n dimensional space if for all pairs of points x 1 and x 2 in the set, the straight line segment joining them is also entirely in the set. So, what we say is a set of points or a region is defined as a convex set in n dimensional space if for all pairs of points x 1 and x 2 in the set, the straight line segment joining them is also entirely in the set. For example, consider this region. You take any 2 points within this region, join them by a straight line, the line will always lie within the region. So, this is a convex region, or the points will constitute a convex set. Whereas, here it is possible that you can take 2 points and the line segment joining these 2 points will not lie entirely within the region. So, this is a non-convex region and the points constituting this region are non-convex set. So, formally the mathematical statement of a convex set is as follows. We say a set C is convex if for any 2 points x 1 and x 2 in the set C, the line segment given by alpha x 1 plus 1 minus alpha into x 2, where alpha lies between 0 to 1 also lies in the set C. So, we say a set C is convex if for any 2 points x 1 and x 2 in the set C, the line segment given by alpha x 1 plus 1 minus alpha into x 2 also lies in the set C. Here alpha lies between 0 and 1. So, this basically represents the linear combination of x 1 and x 2. The convex region may be closed or bounded by a set of functions or may be open, that is unbounded. The intersection of any number of convex set is also a convex set. So, now let us introduce the definition of convex function and concave functions. A function is called concave over a region R if this condition is satisfied. What is this condition? Consider 2 points x a and x b in the region. Consider a number theta which lie between 0 and 1. Then the function value of theta x a plus 1 minus theta x a, if greater or equal to theta into f of x a plus 1 minus theta into f of x b, then the function f is concave over the region R. So, a function is concave over a given region R if f of theta x a plus 1 minus theta x b is greater or equal to theta into f of x a plus 1 minus theta into f of x b. The function is strictly concave if this greater or equal to sign is replaced by strict greater than sign. Similarly, we can define the convex function as follows. A function is called convex over a region R if f of theta x a plus 1 minus theta x b is less or equal to theta into f of x a plus 1 minus theta into f of x b, where x a and x b belongs to the region R and theta belongs to 0 and 1. So, basically you have to take 2 points over the region R, then make a linear combination of these 2 points such as theta x a plus 1 minus theta into x b. Now, evaluate the function at theta x a plus 1 minus theta x b, then function value at x a and function value at x b. Then you can say the function is convex if f of theta x a plus 1 minus theta into x b is less or equal to theta into f of x a plus 1 minus theta into f of x b. Again, the function will be called strictly convex if the less or equal to sign is replaced by a strict less than sign. When you have a single variable function, if the second derivative is less or equal to 0, the function is concave. So, if a function of x, if del square f del x square is less or equal to 0, the function is concave. Similarly, if the second derivative is greater or equal to 0, the function is convex. So, if the second derivative is strictly less than 0, the function is strictly concave. If the second derivative is strictly greater than 0, the function is convex. So, note the figure of or the graph of a concave function. Now, if you take any 2 points on this concave function and join them by a line, this line segment will always lie below the concave function. So, you take any 2 points on the concave function, join them by a line, the line will always lie below the function. This is the property of a concave function. Now, let us look at convex function. For convex function, the second derivative is greater than 0 for strictly convex function. Again, if you take any 2 points on the convex function, join them by a straight line, the line will always lie above the convex function. So, for convex function, the line will always lie above the convex function. What do you say about a straight line? Note that straight line is both convex and concave. How do you determine about convex and concave functions when we talk about multivariable functions? For a multivariate function f x, the condition of convexity are as follows. For a multivariable function, you determine first the Hessian matrix. If the Hessian matrix is positive definite, the function is strictly convex. If the Hessian matrix is positive semi definite, the function is convex. If the Hessian matrix is negative definite, the function is strictly concave. If the Hessian matrix is negative semi definite, the function is strictly concave. Sorry, function is concave. Now, how do I know whether the Hessian matrix is positive definite or semi definite, and so on and so forth? So, if you take any non-zero vector x and find out x transpose H x, this will be a quadratic. So, you take any non-zero vector x and evaluate x transpose H x. For strictly convex function, that means positive definite Hessian matrix, this x transpose H x will always be greater than 0. For positive semi definite matrix, x transpose H x will be greater or equal to 0. For negative semi definite matrix, x transpose H x will be less than 0, negative semi definite, it will be less or equal to 0. We can also say these positive definite or positive semi definite properties looking at the eigenvalues of the Hessian matrix. So, for positive definite Hessian matrix, all the eigenvalues are greater than 0. For positive semi definite Hessian matrix, eigenvalues are greater or equal to 0. For negative definite Hessian matrix, all eigenvalues are less than 0. For negative semi definite Hessian matrix, all eigenvalues are less or equal to 0. A convex set is formed by a plane cutting a convex function. So, this is a convex function, this plane cuts the convex function and you get a convex set. The convex and concave functions play an important role. So, it is important to know whether the function I am optimizing is convex or concave or non-convex functions. If we know that in a given region the function is convex, I know that there will exist only one minimum. Similarly, if I know in a given region the function is concave, there is a single maximum. So, local optima and global optima are same for convex and concave functions, but for non-convex function you will have multiple optimum points. There will be local optimum, there will be global optimum. Let us consider a function f equal to x 1 into x 2. Is this function convex or concave or neither convex nor concave? So, find out the Hessian and you find it the Hessian as 0 1 1 0, the eigenvalues are 1 minus 1. So, one eigenvalue is positive, another eigenvalue is negative. So, this is neither positive semi definite nor negative semi definite, it is indefinite. So, the function is neither convex nor concave. Let us look at another example, f equal to x 1 cube plus x 2 to the power 4. Again evaluate the Hessian matrix and we get the Hessian matrix as 6 x 1 1 1 12 x 2 square. So, the eigenvalues are 6 x 1 and 12 x 2 square. For a given value of x 1 and x 2, I can find out the eigenvalues. Now, look at the eigenvalue 6 x 1 and 12 x 2 square. The eigenvalue 12 x 2 square is always positive if x 2 is positive. If x 2 is 0, it is 0. So, it is never negative, but the other eigenvalue 6 x 1 will be positive if x 1 is positive will be 0 if x 1 equal to 0, will be negative if x 1 is less than 0. So, one eigenvalue is non-negative, the other eigenvalue may be greater than 0, equal to 0, less than 0. So, the function value is neither convex nor concave, because the Hessian matrix may be indefinite. Finally, let us take an example with 3 variables x 1, x 2 and x 3, and this is the function 3 x 1 square plus 2 x 2 square plus x 3 square minus 2 x 1 x 2 minus 2 x 1 x 3 plus 2 x 2 x 3 minus 6 x 1 minus 4 x 2 minus 2 x 3. So, find out the gradient, find out the Hessian. Hessian is a symmetric matrix, all diagonal elements are positive. So, we have to now find out whether this Hessian matrix is positive definite or negative definite, etc. We have done so far using eigenvalues, you can find out the eigenvalues here also. You can also see whether all the leading principal determinants are positive. If they are positive, then Hessian is positive definite matrix. So, how many leading principal determinants are there? One is 6, another is this, and finally the Hessian itself. So, all these leading principal determinants are positive, strictly positive. So, Hessian is a positive definite matrix, which implies the function f is a convex function. If you find out the eigenvalues, you will see that all eigenvalues are strictly positive. So, the function given is a convex function. With this, we stop lecture 12 here.